And I'm now really sorry for Don because he has now to answer all the questions he promised to answer today. And that will be probably a challenge. I would like him again thank very, very, very much for coming here and for not just only talking about the things he's world famous for and the things he knows cold, but to have the courage and confidence to talk about things computer scientists rarely talk about. The courage and openness to share with us his personal journey on that road on which we all always be seekers, where we ask questions about ourselves, about our community, about meaning of the life in general and meaning of the life for ourselves. You came here, Don, to share with us the insights that stem from your journey as mathematician, as computer scientist, as artist, and as Christian. And I would like to thank you very, very much for that. We don't want to leave you without anything, so we thought, first of all, one of the most important things is bring the beauty of MIT back to Stanford. And we also thought you never have actually worn anything white. And so we decided to actually give you that T-shirt to remind you of the time at MIT. There's all the sports there. Please wear it on Stanford campus to show MIT has something embodied to offer to. And to not forget the time here, we would also like to give you that brief history of MIT. And again, thank you very much.
Well, thank you very much, Anna, and thanks to all of you for sticking with me until the end here. I have to confess that when I made up the table of contents for these lectures during the summer, I had almost no concept of what I might say in the last one. But I figured if I had 2 months' time at MIT to come up with something, and if I only keep my antennas open and tuned, I might pick up some appropriate ideas. Well, sure enough, there's no shortage of stimulating ideas that relate God and computer science. I hope I'll be able to explain today some of the ones I think are most interesting and important. In fact, I thought of more than enough things to say in one lecture, and I had to rank order them, so I probably won't have time to talk about the one thing that I promised last week that I would say. Anyway, lots of people have, of course, written about God and science in general. Shortly after my arrival here, I went to a dinner hosted by a thriving local organization called the Faith and Science Exchange, celebrating its 10th anniversary. Since the early 1980s, the University of California in Berkeley has had an active Center for Theology and the natural sciences. But computer science is an unnatural science. Computer science deals with artificial things not bound by the constraints of nature. When I chose the title of this lecture, I had a gut feeling that computer scientists can shed some new light on the subject in addition to the fine contributions already made by biologists, physicists, and other scientists as well as theologians. Because I think computer science gives us new analogies and theories that can help us to understand God. For example, when Arthur Peacock wrote 20 years ago about creation and the world of science, he compared God to the composer of a symphony, writing music that obeys fixed laws but contains random elements. Peacock saw God as an improviser of unsurpassed ingenuity. Music is indeed a useful analogy because it's a flexible form that moves through time, but certainly computer programs are much richer in this respect because programs not only move through time, they also interact with people and they can also modify themselves. When I talk about computer science providing possible insights about God, of course I'm not thinking about God as a super smart intellect surrounded by large clusters of ultra-fast Linux workstations and some great search engines. That's the user's point of view. I'm thinking about the science part of computer science, the abstract notions of processes, the theories that computer scientists have been developing about how to deal with large quantities of non-uniform data in dynamic ways. Such things are much better understood now than they ever have been before, and they clearly have intimate connections with God's role as creator and sustainer of the universe. Furthermore, computational models are better able to describe many aspects of the universe better than any other models we know. All scientific theories can be modeled by programs. Years ago, I was pondering the difference between science and art. People have been asking me why my books were called The Art of Computer Programming instead of The Science of Computer Programming. And I realized that there's a simple explanation. Science is what we understand well enough to explain to a computer, and art is everything else. So every time science advances, part of an art becomes a science, so art loses a little bit, but mysteriously, art also seems to gain back again, because as we understand more, we think of more things that we don't know how to explain to computers. During the panel discussion a few weeks ago, it developed that a lot of people in the audience, maybe a majority, thought that it wouldn't be long before science catches up with art and there won't be any art left. We'll be, according to that opinion, we know how to program a robot that would be able to do everything the people on the panel could do. And also the people in the audience, I guess. Now, I personally see no signs that any such thing is on the horizon, but I do want to mention a point that Brian Hayes brought up earlier this year in American Scientist. Hayes observed that if we can create such robots, those robots would also be able to create such robots, and so on. And you see, this would increase the likelihood that we ourselves were created by some designer. In any case, I do think people who write programs do have a glimmer of extra insight into the nature of God for that very reason, because creating a program often means that you have to create a small universe. For example, I spent most of this year writing programs to simulate a new computer called MMIX. One of those programs was perhaps probably the most difficult that I've ever written. And I thought hard about how it would be to live with such a machine and with the new tools that I was creating, sort of like living in a new subculture. A week from today, I'm going to be talking about that computer. I think it's fair to say that many of today's large computer programs rank among the most complex intellectual achievements of all time. They're absolutely trivial by comparison with any of the works of God, but still, they're somehow closer to those works than anything else we know. My main point, though, is not to debate the merits of computer science, but I do want to discuss some of the things that our experiences with computers during the past 50 years have taught us. First, I want to mention the fact that computing gives us great appreciation for the size of finite numbers. Now, I spoke about this many years ago at a big meeting of the American Association for the Advancement of Science in Boston in 1976. My paper was called Coping with Finiteness, and it was later reprinted in several books. I hate to repeat myself, but I suppose some of you here today were unable to hear my talk in 1976. And maybe you never read the paper either, and even if you did, you probably forgot about it. So I'm going to spend the next few minutes repeating some simple but eye-opening facts about finite numbers. So I want to start small and remind you that x times n means x plus so on, the sum of n copies of the number x. Similarly, we can talk about x up arrow n, which is the product of n copies of x. For example, 10 up arrow 10 is 10 times 10 times 10 times 10 to 10 and so on. It's 10 billion. Now, people usually write that as 10 to the 10th, but I like to write it with an arrow because of the next step, which uses two arrows. And so if you have two arrows, x double arrow n, that means you take x to the x to the x to the x to the x. Now, this arrow notation is my big claim to fame because it's what got me into the Guinness Book of World Records. Anyway, 10 double arrow 10 is that number, which you see is 1 followed by this many zeros, okay? All right, so now that's a fairly large number. Now, I mean, if you put a monkey down at a typewriter and wait until he types out perfectly the entire text of Hamlet, it's only 1 followed by about 40,000 zeros. So this is 1 followed by quite a few zeros. But anyway, that's 10 double arrow 10. Now the general rule, of course, is that if you have k arrows, x k arrows n, you just define it as the k minus 1 arrow thing over and over again, all right? So I want to give you an example of a small example of the arrow functions so that you can understand about these finite numbers, and I'm going to look at 10 quadruple arrow 3, okay? Now, so of course, by definition, that means 10 triple arrow 10 triple arrow 10. And so we first have to evaluate 10 triple arrow 10. Well, 10 triple arrow 10, of course, is 10 double arrow 9. So that means this. Okay. So now you see we just expanded the 10 double arrow 10 there and replaced it by what it is. All right. So there we are. Now, so now let's go one more line. You see what's coming up here. I can get rid of one more here, and we just have to have how many zeros are there in that guy? Wait a minute, I lost. There must be a typo here. I got to lose one more. I got to lose one more double arrow. I just pay myself $2.56. Okay, take out one of these 10s here. But you see the stack of 10s is 10 double arrow 10 levels tall. Now that's such a, I can't even tell you how big that stack of 10s is without using double arrow notation. All right, so anyway, that's a huge number, and I can't even write it down. But then we repeat the double arrow operation again, getting even huger number and so on, and finally we get this thing evaluated, and I'm calling this final result very fancy K. In fact, if you look at my book with a magnifying glass, you'll see that I worked hard to make I mean, it was such a big number, I just couldn't use an ordinary letter for it. Now, of course, we're not done yet. That's just 10 triple arrow 10. I have to, in order to get the final number that I started with, 10 quadruple arrow 3, I have to take 10 triple arrow to this fancy K. Now that is, of course, the double arrow operation repeated fancy K time. Now, if you stop to think about this, I think if anything is mind-boggling, it's incredibly large. You cannot believe how large it is. And I said here the three dots suppress a lot of detail. Maybe I should have used 4 dots. But anyway, if you don't think this number is as large as being beyond human comprehension, I can at least say definitely that if you consider all the numbers less than or equal to this number, almost all of them are impossible to describe in any way in the universe, because we know that most numbers description is incompressible. So anyway, that's of course that's a very small as finite numbers go. Almost all finite numbers are bigger than this, but this big enough for me. This big enough for me, and if you can really thinking about it, you realize that just being finite isn't that much of a limitation. Now I'm going to call this number super K, this 10 quadruple arrow 3. I'm going to call it super K. When you start to comprehend the immensity of super K, you see how pointless are the philosophers' discussions about finite versus infinite. Infinity is a red herring. I would be perfectly happy to give up immortality if I could only live for super K years before dying. In fact, super K nanoseconds is enough. Now, okay. So now many years ago, I learned about Cantor's famous theory about higher orders of infinity. I learned the beautifully simple fact that the set of all ways to label the elements of any given set with zeros and ones always has strictly more elements than the given set has. And I once thought if I ever had to preach a sermon in church, I would try to explain Cantor's theorem to my non-math friends so that they could understand something about the infinite. But now I realize that infinity is not necessarily even one of God's attributes. I'm quite willing to grant that God might indeed be infinite and might have the power to examine infinitely many possibilities in an instant. But even the ability to deal with numbers on the order of super K is more than enough to inspire awe. Moreover, I don't think theologians can really disagree with me on this. To say that God's abilities are not infinite but limited by quantities like super K is not a realistic limitation at all. Such a limitation cannot contradict the Bible or any other sacred text because natural language has no words to distinguish meaningfully between such unimaginably large magnitudes. For example, the word infinite itself occurs only 3 times in the King James Bible. The first time is when one of Job's comrades says, "Job, your iniquities are infinite." In the second place is God's understanding is said to be infinite. And in the third place, the power of Egypt is said to be infinite. Now, only the second of these 3 applies this attribute to God, and the Hebrew words in that verse can be more accurately translated as too big to count. So the amount of academic hair-splitting about finite versus infinite in the literature is itself too much to count. But it misses the point. The real point, I think, is made rather well in Psalm 139. O Lord, you have searched me and known me. You discern my thoughts from afar. Even before a word is on my tongue, lo, O Lord, you know it altogether. How vast is the sum of your thoughts. If I would count them, they are more than the sand. In other words, God knows incredibly more than we can understand. Now, I grew up with the idea that God constantly reads my mind, and I've always been comfortable with that invasion of my privacy. As a result, I haven't been especially successful in cryptographic research about keeping secrets. Now, of course, I don't understand how it's possible for God to read my mind or to penetrate anybody's consciousness, especially because every individual brain probably has its own code for information processing. But that doesn't make me disbelieve that God can do it, even if we limit God to being a finite capacity of size super K. Peter Gomes has wisely described the Bible as an effort to cram into the human imagination the unimaginable immensity of God. But he didn't mean to imply that the Bible makes technical distinctions about subtle mathematical details. Another thing about finiteness is, I'd like to show you, is based on a rather deep result of computer science, which came out of an MIT thesis, Larry Stockmeyer's thesis in 1974, joint work with Albert Meyer on this particular problem. Here, well, I guess I can put this whole slide up. Here's the. I don't want to talk too much about it, but there's a theorem of Buchey that says that certain statements about the positive numbers can be proved or disproved in a finite amount of time. And people technical in the audience, this is weak second-order arithmetic. Now, if you take a sentence of length 617 in weak second-order arithmetic, you can express it in terms of 64 symbols, including a blank space if it's a short statement. And the statement might have some quantifiers for all x there exists something or other. But it's some logical statement. And then there's an algorithm that will tell whether or not the statement is true or false. And you could build it into a circuit, and you would start out with a 6-bit encoding of each of the symbols, or the 617 symbols, and then outside, and or not gates in here, and out comes the answer, true or false. This statement was true or false. And according to Buchey's theorem, you can construct such a circuit with finitely many components, finite amount of time. But what Meyer and Stockmeyer proved is that every such circuit must use at least 10 to the 125th components, which is larger than the number of protons and neutrons in the entire known universe. And you change 617 to 618, it gets harder again. So you see, there are limitations on of complexity of certain computational problems. I think it's fair to say that God may well be bound by certain laws of computational complexity, even if we grant, as I do, that the Bible is God's inspired word. The Bible doesn't deal with Bucky's theorem or any such fine points of detail, or was it ever intended to. Computer scientists today know many things about all kinds of levels of incredible difficulty that are inherent in the solution of different kinds of computational tests, even when those tests are solvable in finite time. These theoretical results could be used in academic discussions to restrict God's ability to be all-knowing and or all-powerful in certain ways if we assume that God has finite resources of a certain size. But I don't recommend that theologians undertake a deep study of computational complexity unless they really enjoy it. Because the fact is, God can know much more than enough and can be plenty powerful enough to do anything relevant to the universe without being strictly all-knowing or all-powerful. Finiteness is not a limitation in practice. So when I say that the question finite or infinite is a red herring, I don't mean simply that philosophers and theologians have often been arguing about an unimportant issue. I also mean that physicists and other scientists fail to realize this. For example, take the literature of chaos theory. Hundreds of papers have been written about the behavior of solutions to unstable recurrences by people who assume that real numbers are real. Let me explain to non-mathematicians in the audience. When a mathematician talks about real numbers, they mean decimal numbers that have infinite accuracy, infinitely many decimal places. Well, the fact is, real numbers are an abstraction. They're an immensely useful abstraction. The concept of real numbers allows us to use calculus, other tools of mathematics to deduce all kinds of useful things. But it's a tremendous leap of faith to assume that real numbers apply perfectly to the real world. To assume that two physically realizable objects could be in different places even though their positions agree up to super K decimal places. I can understand why people unconsciously make this assumption. All the textbooks start with real numbers. It's a familiar concept, easy to work with. Similarly, after I learned geometry in high school, I thought I knew what parallel lines were. You take any line and a point off that line. Well, then that line and the point determine a plane, and in the plane there's exactly one line through the point that's parallel to the other line you started with. Parallel means never intersects that line. Now, it seems obviously true. It's called Euclid's fifth postulate, Euclid's parallel postulate. Well, years later, I learned about non-Euclidean geometries which satisfy other axioms stated by Euclid, but not this parallel postulate. In some geometries, there can be two or more lines parallel to the given one. In other geometries, there aren't any at all. Now, I thought this was an amusing curiosity, but I never believed for a moment that non-Euclidean geometries had anything to do with reality. The possibility didn't even occur to me, since I knew that the universe was Euclidean. Maybe 20 years went by before I was shocked to realize that I had no grounds for that hypothesis at all. Euclid's law was convenient for the practical calculations I needed, but it wasn't good enough for astronomers who were faced with the actual properties of the real world. Some years ago, I wrote a book about so-called surreal numbers, which are much richer than real numbers because they include not only the real numbers, but also in infinitesimally small quantities, as well as numbers like infinity raised to the power of square root of infinity, and many other, they're closed on, they're algebraically closed and closed under, you can add and subtract, multiply. Surreal numbers, in a sense, surreal numbers are actually simpler than real numbers are. For example, you can define surreal numbers with only two very simple axioms. I suspect that if physicists had been trained since childhood to work with surreal numbers, they would implicitly imagine that surreal numbers describe the actual universe we live in. It seems to me that a new branch of physics is needed, called maybe discrete physics or something like that, to study the effects of the assumption that parameters can be infinitely precise, and to consider instead that the universe probably has only a finite but extremely large number of states. I've heard of a few people who are working on this. It seems to me that such ideas deserve to get into the mainstream. Plato once said, "I have never known a mathematician who was able to reason." I think he was referring to the fact that mathematicians tend to believe that their abstractions apply perfectly to the world, to a world that's more complex than they can imagine. On the other hand, according to James Jeans, nature abhors accuracy and precision above all things. Well, I can't dwell any longer on this because I also want to cover several other ideas today. The next topic I want to discuss is John Conway's game of life as an example of an artificially created universe. This is probably the simplest example of a cellular automaton that's really interesting. It's an idea that John came up with about the same time that he invented surreal numbers in the 1960s. We can imagine a grid that consists of square cells extending arbitrarily far in any direction. At every instant of time, each cell is either off or on. And in this picture here, the black ones are on and everything else is off. There's a simple rule for determining the state of each cell at the next instant of time based on the current state of the cell and its 8 neighbors. So suppose k of the neighbors are on at a given time. In t, then at time t plus 1, the next time the cell is off if k is less than 2 or greater than 3. If you don't have enough neighbors, you have too many neighbors, you're off. But if k is exactly 3, you have exactly 3 neighbors, then the cell goes on. And if you have exactly 2 neighbors, the cell stays as it was before. Now, this configuration that I've got on the screen here is one that Bill Gosper made up November 1997. It's called a totally aperiodic glider wave. Let me show you what happens, for example, after 1 unit of time. You see that things like this has no neighbors, so it's going to go away. Some of these here have too many neighbors, they're going to go away too. The ones that have 2 neighbors are going to stay as they were. The ones that have 3 neighbors are going to go on. And after 1 step, you get a pattern like this. And there's wonderful resources on the web about the Conway's game of life. You just go to your favorite search engine and say Conway Life, you know, there's terrific Java applets. You can watch this to your heart's content and see. And people have said even in the 70s that more computer time was spent simulating this game than maybe anything else. Many companies banned doing this because it was chewing up so much time. It is really fascinating to watch what happens. Well, in this particular case, after 100 units, after 100 steps, these things start to send out so-called gliders, and the gliders come in a really interesting pattern. And the reason this is called totally aperiodic is because if you look at the states of any cell whatsoever, it's not periodic. No cell by itself could be described by a finite automaton. I could give several lectures concerning lessons about real life that could be learned by studying examples of artificial life like this. I have time to only mention a few of the main points. First thing, it's abundantly clear that a programmer can create something and be totally aware of the laws that are obeyed by the program and yet be almost totally unaware of the consequences of those laws. Running the program with different starting configurations often leads to really surprising new behavior. Secondly, the game of life illustrates the power of evolutionary mechanisms. Stable configurations arise out of random soup very quickly usually, and many of those configurations have properties analogous to biological organisms. There's a glossary of hundreds of names for such things on the web. There's ants, bookends, bunnies, caterers, eaters, fish, gliders, as I showed you, light bulbs, and so on. But the thing that strikes me most about this game is the fact that it's obviously deterministic. I think it sheds light on the age-old question of free will versus a deterministic universe. At least it's helped me a bit with this issue. Somebody, I don't remember who it was, maybe Conway himself, told me in the 1970s that the computer-simulated behavior of patterns in this game tend to be so lifelike that it actually gave him pangs of conscience whenever he would shut the computer off or set it to work on something else. He was killing off the creatures before those creatures had fulfilled their potential. But Conway's game of life is completely deterministic. All the future generations of every pattern, just those simple rules of 2 and 3 neighbors, all the future generations of every pattern must exist whether we simulate them or not. They can't die. Pulling the plug before a computer counts up to 1,000,000 doesn't harm the number 1,000,000. So now let's imagine that the universe is totally deterministic, the real universe, and finite, but of course extremely large. Conway and Gosper proved that the game of life is universal in the sense that this game can simulate anything that is computable by deterministic laws. Therefore, in principle, we could set up a gigantic on-off pattern that would perfectly describe the future of the entire universe starting at any given state if we simply followed Conway's rules. In fact, we could do this on a finite two-dimensional game board that was not much larger than the number of entities in the universe itself. The simulation wouldn't run in real time. In fact, it would be mighty slow. But it wouldn't miss any detail. That's what a deterministic universe is like. Such a universe exists without needing to be simulated, in the same sense as any number exists without needing to be named. Raymond Smullyan's short story, Planet Without Laughter, ends with a discussion of free will. I actually like the early parts of that story better than the ending, but he's entitled to his opinions, and here's one of the things he said. He said, Smulyan, humans are like children. The only way you can get them to do anything is to make them think that it is they who are doing it. Their pride is so great that without having the illusion of free will, they will never go forth and amount to anything. And then I'm not sure if it was God in his story was saying this. I think so. So he's saying that we don't have free will, but we think we do, because otherwise it would be bad. So apparently then the illusion of free will is good enough. Maybe what Smulyan is saying, because it's essentially indistinguishable from actually having free will. Just like pseudo-random numbers are just as good as truly random numbers for all practical purposes. Well, if that is true, the illusion of free will could even have evolved by Darwinian principles. Einstein didn't believe in freedom of the will. He said, "This awareness preserves me from taking too seriously myself and my fellow men as acting and deciding individuals, and from losing my temper." Here I cannot agree. Such thoughts are so totally different from my own that when I first read them I thought they were self-contradictory. If lack of free will kept Einstein from losing his temper, he didn't have any temper to lose. You don't decide whether or not you have free will if you don't have the power to make decisions. But after thinking about it some more, I had to admit that such a viewpoint is indeed logically consistent, even though I don't subscribe to it myself. In my own view, people ought to take responsibility for the things they choose to do, and I think I can learn to control my temper about other people's choices without believing that they had no choice. Indeed, it seems impossible to me to be a parent and to observe one's own children without believing in free will. The traditional argument against free will by some theologians is that God cannot know everything without knowing what choices we're going to make. Now, this debate goes on, but I think the evidence for that argument is fairly weak because of the inadequacies of natural language to deal with such technicalities in a precise way. It seems much more likely to me that God is interested in our decisions and that he purposely held back from asserting total control. Why write a program if you already know the outcome? As a software designer, I greatly enjoy watching surreptitiously what other people are doing with the programs I've written. Well, sometimes I wince, too. It's similar to the feeling that parents have when their children are developing attitude. Sometimes they're very happy about it. Sometimes they're alarmed, but it's always interesting. Dorothy Sayers said that she enjoyed writing plays better than writing novels because the actors and actresses would reveal deeper meanings that she hadn't specifically planned. Now, to carry this discussion further, I need to talk a little bit about quantum mechanics. Several years ago, I chanced to open Paul Dirac's famous book on the subject, and I was surprised to find out that Dirac was not only an extremely good writer, but also that his book was not totally impossible to understand. The biggest surprise, however, actually a shock, was to learn that the things he talks about in that book were completely different from anything I had ever read in Scientific American or in any other popular account of the subject. Apparently, when physicists talk to physicists, they talk about linear transformations of generalized Hilbert spaces over the complex numbers. And observable quantities are eigenvalues and eigenfunctions of Hermitian linear operators. But when physicists talk to the general public, they don't dare mention such esoteric things, so they speak instead about particles and spins and things which are much less than half of the story. No wonder I could never really understand the popular articles. The extra detail that gets suppressed when quantum physics gets popularized amounts to the fact that according to quantum mechanics, the universe actually consists of much more data than could ever be observed. For example, Dirac's preface states that nature's fundamental laws do not govern the world as it appears in our mental picture in any direct way, but instead they control a substratum of which we cannot form a mental picture without introducing irrelevancies. Quantum theories are almost exactly 100 years old now, and they seem to be holding up rather well, even though Dirac's book first came out in 1930. James Jeans explained the need for quantum physics in this way. At the end of the 19th century, it first became possible to study the behavior of single molecules, atoms, and electrons. The century had lasted just long enough for science to discover that certain phenomena, radiation and gravitation in particular, defied all attempts at a purely mechanical explanation. While philosophers were still debating whether a machine could be constructed to reproduce the thoughts of Newton, the emotions of Bach, or the inspiration of Michelangelo, the average man of science was rapidly becoming convinced that no machine could be constructed to reproduce the light of a candle or the fall of an apple. Well, I can't give you a tutorial about quantum mechanics today, but I do want to mention it because a lot of computer scientists have been working together with physicists for the past several years to develop something called quantum computing. These concepts have not yet been proved, but steady progress is reported, and it's not impossible that quantum computing could turn out to be a truly revolutionary breakthrough, perhaps allowing us to deal with exponentially many possibilities in linear time. I'll try to describe the situation as simply as I can without speaking of eigenvalues, but still I hope I can convey some of the essence of these ideas. Every year at this time, for the past 6-7 years, I've traditionally given a so-called Christmas tree lecture at Stanford, dealing with some aspects of tree structures. Tree structures rank among the most, the computer scientists' most loved concepts. Now, keep in mind that this is an idealization and oversimplification, but we have to start somewhere. Imagine starting at the top of this diagram, which represents a branching point where some choice has to be made. Also imagine that going to the left or going to the right will affect the entire future history of the universe. First, the effect will be very small, but eventually the effects will build up. After the first choice, say we go to the left, another decision has to be made, maybe go to the right, and then another, and so on. So the number of possible destinies for the world goes from 2 to 4 to 8 to 16, 32, and so on. If any of you saw the movie Run, Lola, Run that came from Berlin this year, does anybody know that movie? Yeah? Okay. You have a clearer idea of what I'm saying. That movie, there's 3 parts to that movie, and all 3 parts start out almost the same, except maybe she's 1 second later in the second part and 2 seconds later to start in the third. something like that. And but then what happens in the three parts? Completely different ending, and completely different in the middle as well. And in one case, the heroine dies. In one case, her boyfriend dies. In the other case, it's happily ever after. But it's a fun movie, but it can give you some idea about what I'm saying here about changing the state of the universe with small changes. All of the paths in this tree are consistent with the laws of quantum mechanics. The most popular way to account for what we can see in physical experiments is to imagine flipping a coin at each branch point. Einstein made a famous comment that God doesn't play dice with the universe. And he held to that position for the last 30 years of his life. But nowadays, that's definitely a minority opinion. For example, Rustum Roy gave a major lecture in London 20 years ago called Living with the Dice-Playing God. David Bartholomew's book of 1984, called God of Chance, said that God uses chance because it offers many advantages which is difficult to envisage being obtained in any other way. For example, in genetic evolution. Indeed, computer scientists have proved that certain important computational tasks can be done much more efficiently with random numbers than they could possibly ever be done by any deterministic procedure. Many of today's best computational algorithms, like methods for searching the internet, are based on randomization. Some people, of course, are very suspicious of random choices. For example, Hugh Montefiore in 1985 said, "Chance and necessity may produce creativity, but they cannot produce purpose." I believe he was dead wrong. I use random numbers all the time with a very definite purpose to help me discover something. John Peacock's opinion is that God has perfect knowledge of the probabilities of events like radioactive decay, but he doesn't have knowledge about the outcome of those events, just of the probabilities. And he also says that God created such a universe intentionally. Stephen Hawking said earlier this year, "All the evidence points to God being an inveterate gambler who throws the dice on every possible occasion." Well, the picture isn't quite as simple as you might think, however, because quantum theory also implies that the probabilities aren't necessarily independent of each other. They're said to be entangled. In fact, quantum theory insists that certain observations have to agree even though they are individually random, and even though they're being made simultaneously in two completely different parts of the universe. Mind-boggling as it seems, quantum mechanics requires action at a distance, as if there was instantaneous communication much faster than the speed of light, in spite of what you may have been taught about the theory of relativity. Yet quantum mechanics doesn't contradict the theory of relativity, because these widely separated events are individually random. Professor Abner Shimoni of Boston U says that there's peaceful coexistence between those two theories, because he says there's not really action at a distance, but passion at a distance, because of the way constraints on the way that entangled choices reveal themselves. Well, exploiting the counterintuitive properties of entanglement is the basis for hopes about quantum computing, because perhaps entangled choices can be coerced to run through many possibilities quickly and to sort out the good ones based on some kind of resonance. I can't claim to understand much at all about entangled bits, but for me the significance of the probabilistic model for quantum theory is that it clearly makes room for free will, and it allows God to exert dynamic control over the world without violating any laws of physics. In other words, we can think of God as a tree pruner, occasionally influencing the outcome of various branches while simultaneously adjusting the non-observable information behind the scenes so that all observations remain consistent with quantum mechanics. And we ourselves, even us, our spirits or souls or minds, whatever you want to call this part of our being, we might be little tree pruners also, with much more limited and local powers, of course, but still able to exercise free will in this way. Who knows? Such a thing might even be easy if God sets us up behind the scenes with some useful hardware somewhere off in the hidden dimensions. James Jeans said in 1930, "For aught we know, or for aught that the new science can say to the contrary, the gods that play the part of fate to the atoms of our brains may be our own minds." Last Sunday I heard another relevant quotation, this one from Martin Luther King Jr. "We, through our deeds and words, our silence and speech, are constantly writing in the book of life." Well, in closing, I want to say a few words about consciousness. If I can find it. Stuart Sutherland, in the 1996 edition of the International Dictionary of Psychology, gave a great definition of consciousness. Here's what he said: "Consciousness is the having of perceptions, thoughts, and feelings awareness. The term is impossible to define except in terms that are unintelligible without a grasp of what consciousness means. Consciousness is a fascinating but elusive phenomenon. It is impossible to specify what it is, what it does, or why it evolved. Nothing worth reading has ever been written about it." Okay. Well, during my visit to here at MIT, I did find one book about consciousness that was at least partly worth reading. It was called Mind and Matter by physicist Erwin Schrödinger. Schrödinger's main insight was to equate consciousness with learning. After you've learned something, you do it unconsciously. Yet consciousness remains the largest major question about which science has so far made little or no real progress. Computer scientists studying artificial intelligence may well have the best chance of unraveling this mystery if it ever can be demystified. The most promising approach that I've heard of is the notion that consciousness might be a kind of genetic algorithm in which a large pool of ideas is constantly competing for attention in our brains. These ideas fertilize each other, and the fittest survivors continue the process in Darwinian fashion. As I'm talking to you now, there's all kinds of survival going on inside our heads. Maybe something like that is going to work out. It seems to have some of the right properties, but maybe still the reins will still have to be controlled by some free spirit outside of the observable portion of quantum mechanics. As Peter Gomes has said, we experience close encounters of the transcendental kind that suggest relationships beyond the power of our experience to reckon, but which we know in some fundamental way to be true. Please excuse me for giving so many quotations. As I was preparing these lectures, I ran across lots of things that were said better than I could say them myself, and couldn't resist giving you the benefit of these other people's wisdom. I'd like to conclude by quoting one more thing from the end of the talk that James Jeans gave about a similar topic. He said, "Every conclusion that has been tentatively put forward in this lecture is quite frankly speculative and uncertain. We've tried to discuss whether present-day science has anything to say about certain difficult questions which are perhaps set forever beyond the reach of human understanding. We cannot claim to have discovered more than a very faint glimmer of light at the best. So our main contention can hardly be that the science of today has a pronouncement to make. Perhaps it ought rather to be that science should leave off making pronouncements. The river of knowledge has too often turned back on itself." Well, I have to add, yes, maybe we should stop making dogmatic pronouncements, but we don't stop trying to learn more. So thank you for listening. I'm ready for questions. Well, if there are no questions, there's one in the back, guy.
Yeah, I've got a comment. 22 years ago, I took a course when I was a graduate student here at MIT. And the title of the course is Digital Physics. It was taught by Ed Fredkin.
Digital Physics by Ed Fredkin. Yes,
Yeah.
he's the main person. I was one of the three people I had in mind when I said that, okay.
I vividly remember a discussion in class about the possibility of a cellular automaton model for the universe. And Fredkin spoke rapturously, I think, of electrons perhaps being represented by billions of cellular automaton cells in some 3D framework. One of the students in a very distressed voice said, wouldn't that take an awfully long time? Wouldn't it be awfully slow?
I see.
Fredkin said, how fast do you want it to be? And another student piped up and said, 1 second per second. Which I think was actually a very deep insight.
I see. You don't need, they don't have to be electrons or so on. I mean, yeah, I mean the universe could very well be made out of discrete components, very, very tiny. And Fredkin had thought a lot about that. And other people I know, a man named Poston in Warwick had some very interesting things about this that I read a while ago, and so on. There's, when I study computer algorithms, I have to do this kind of thing all the time. There's always the ideal thing given by the theory, and then there's when you try to apply it to the world. And so I have to say that something is x is equal to y plus big O of z, and the big O is what's missing. I always felt that physicists always make statements. Something is asymptotically this, but they don't say what they don't give the big O. They don't say how big the error is. And I think would be extremely valuable to develop all of the theories of physics with the big O in there, where the big O represents errors in your data and in your answer. Some arguments in mathematics I have not been able to get rid of big O's. I mean, things like the Borel-Cantelli lemma and things like that I don't want to go into, but there are some processes, subadditive functions, that they just are existence theorems. They don't give you any way to compute bounds on what you've done. But I believe that the main theorems, the things that apply to reality, almost always allow you to understand this, the tremendous difference between assuming that something is infinitely accurate or finite but extremely large, like super K, accurate.
And therefore to suggest another answer to the student's question, which is, yes, it's slow, and the slowdown is super K, but that's small as finite numbers go.
That's great, yeah. But also the student, I would say the student is operating at the same speed as the universe. Yeah, hello? Yeah.
And if we can make an assumption that in the distant future, at some point, everything that our nervous system is capable of conceiving will be determined to be deterministic, that we can predict at some point through some mechanism that we may not be able to conceive of right now. Right now it's easy to say the computers are not capable of doing it, etc., but I find that very weak. But even if you could, do you think in some way that could then negate the possible existence of God? That's what to me seems to be one interesting weakness in the way we're trying to use logic to say that if everything is deterministic, then God can't exist.
No, okay. The question is, if the world is deterministic, does that disprove the existence of God? No. It just disproves the existence of free will. Those are different questions. But in fact, this idea that that recording all the state of everything in the world, that seems to be completely beyond the possibilities of present-day physics, because present-day physics uses complex numbers and all kinds of unobservable things that can only be observable if you destroy the information that's hidden. I don't understand how the physicists have this nice theory about the way things work when they're undisturbed, and then they have this theory of what happens when you make a measurement. But I haven't seen what happens when a physicist gets in and, I mean, when you have an equation in there for the physicist taking a measurement. There should be a way to make the picture close on itself the way computer languages do, but that doesn't. But I don't see how. I don't know enough about physics to see that, but it wasn't addressed in any of the books I looked at. A question over here.
This computational complexity and infinities and positing a God that relates to all these issues. How does that have, what does it have to do anything with good, bad, or purpose?
What does these issues of computational complexity have to do with good, bad, and purpose? Yeah, well, that's a terrific question. I didn't address anything about purpose in here except that I said, I use randomness for my own purposes, and I sort of assumed, mistakenly probably, that God would have certain purposes as if he were a human being. So I know that it's not valid to try to second guess God with human concepts, but it's the only way I have of trying to understand things. And there's big questions about why are firemen why do firemen die and so on. Did God shouldn't God have done something so that it didn't happen and so on? Well, we have no idea what would happen if the other branches of the tree were taken. But I'm afraid I haven't got any good answers to this that add to what the people have said over the years about it. I mean, Leibniz said that we live in the best of all possible worlds in the sense that of possible. In other words, Leibniz says God has looked through and seen all worlds that are possible. There aren't very many are possible, but of the ones that are possible, he chose the best. And and it's not our idea of best, but we don't know what's possible and what's impossible. That was his answer. But there's been other people thinking about these things over the years. I don't know if computer science has anything to add. A question from this side? Yes?
What makes you think that the Bible is the Word of God, or is that an axiom chosen at random?
That's an axiom that I tend to find confirmed as I look at it. But I don't treat the Bible literally as axioms, though. I mean, I don't say that the Book of Revelation is a set of axioms or things like that. But I think that the Bible reflects God's messages if we understand the way in which it was written and the process of the historical process, the difficulties of going through thousands of years. I think a lot of I think that's one of the best clues, other than the universe itself, as to what God wants us to do. This is what I was talking about last week. But it's nothing that I would expect that I could persuade anyone else of by a mathematical argument. And there are other religions that I respect very well that I believe God is speaking in their scriptures as well. Question here.
It's hard to express this question. I'm not sure I can find the right terms, but let's take material, what I call material physics, to be those things describable by physics or understandable by physics.
Yeah.
If that is the case, do you see God as standing outside of that universe or as coexisting with part of it?
Yeah, do I see God as standing outside the universe and letting it run? And the answer is no. I see him as a tree. I see him as active all the way through. In fact, I don't. The way I view God myself, you might. It has lots in common with pantheism, where there, God's everywhere. Those concepts, some people think they're diametrically opposed, and actually, in essence, from a computer programming standpoint, I can conceive of distributed computing, but lots of cooperating things that are all really one program. The way I think of an ant colony as a single organism.
Aside from acting on, but interleaved with
Interleaved
this
with,
physics.
yeah, right. I mean,
So that God is material in that sense.
no, it's in another dimension. I mean, do you understand how if we lived in a two-dimensional universe, there would be things that we wouldn't perceive.
Then it'll never be describable by the physics?
They'll never be
Describable
by
observable
physicists. Yeah, that's true. But I don't think that that's bad. I mean, I think that, do you have to know? I mean, if you knew, it would be kind of boring after a week. Yes.
If you have this discrete deterministic model, it's a kind of computer, and we know from the speed-up theory that there's no way to know what's going to happen without it's happening. So isn't that mean that the determinism you have is really quite a bit different than the kind people think of where the universe, where you can calculate like the next position of the planets anytime in the future?
Well, there's this. So what I yeah, well, this is an interesting point as to the classical thing is if a tree falls in the forest and nobody's there to, the forest is in a black hole, did the tree really fall? If nobody has ever named the numbers up to super K, do they exist? I mean, I'm willing, quite willing to believe that the number 5 exists, and 6 and 7 and so on, and all the numbers I can count up to. But does that mean that all finite numbers just have an independent existence? That's what I meant by being deterministic. That it's there. So I mean, it's just like if all the jokes in the world were numbered, and somebody would come to somebody and say 37, and so our universe would be number such and such. Yeah, I was also, there's also I didn't want to go into. There's also this many worlds hypothesis. I tended to think that it's too wild to really be to really even correspond to quantum physics, but some people have used it to account for entanglement, where they say that all of these branches actually are true. Like, in other words, as we're talking, the universe is going on, and in all these branches, like you and I are existing, and all 3 of the things that happened to Lola happened. In some of them, the ending is better than others, and we just, these are all solutions to equations. This is the way, this is the way a computer scientist looks at non-deterministic computation, as if all of them are going on and clones of each other. Now, we have no way to test this hypothesis, so maybe in some of those we we just die earlier, whatever, you know. And then you get the question, what is consciousness? Because the consciousness has to be some kind of a, I mean, each of our individual consciousness has to be attached to every branch of this tree. But these, you know, anyway, there's lots of speculations of this abstract kind that I think we can never really know what they mean. I probably didn't answer your question, but those are some of the complexities that are associated with it. David?
This is sort of a follow-on to the last two questions. Rather than state it in general form, I'm going to ask it as a specific example. Are you part of God?
Am I part of God? That's an interesting thing. What? No. You know, this, I'm not sure exactly what the conclusion are, but you know, it's Christian dogma that God is in us and we're in God. And that is why, for example, like this passage that said, refrain from sexual immorality because you're part of God. In other words, that's part of the, you know, that's part of a motivational thing. But I don't feel that I'm an antagonist of God or something like that, but I still think I have a free will that makes that's independent in some sense of God.
Is there any sense in which it could be true that each of us is all of God?
Is there a sense in which each of us could be all of God? Do you mean each of us individually?
Yes.
Well, I suppose there exists a sense, but I don't know. I certainly don't feel like God. Yes?
The last three questions.
I can't hear.
The last 3 or 4 questions touching on this one is, do you find something in your mathematical understanding of things that gives a demarcation between running an experiment, as the questioner asked back there, and a Gedanken experiment, which really think through what might happen, as Einstein was so far fond of doing?
The distinction between running an experiment and thinking about the experiment. Well, in my thought process, are you assuming that my thought processes are accurate?
I want to know what you're assuming.
You know, mine aren't, but maybe a perfect computer, a perfect creator would be able to go through and wouldn't have to run something. So my view of this thing is that that God is dynamically involved and actively interested in the choices that we make. But as I say, there's no way to prove any of these things. But I see it though like as if I'm you know, it's a weak analogy, but still, as good as we have, like a user of software or something, where, like when Joel Moses had this Maxima system at MIT 20 years ago, and I used to log in from California to use it. And there were always people watching me as I was using it. And I was glad to know that. Because, you know, every once in a while, I type out in my terminal, did you mean to do this? You know, and now that's the kind of attitude that I'm thinking God is using with me in life.
Tie that with the Schrödinger cat problem?
I don't know Schrödinger's cat about. I'm sorry, I've heard a couple of times, and there's something about cat dying, and I hate to think about that. I'm sorry. I don't have time to go into that right now because I've tried before. Yeah, hello?
What are your thoughts on prayer Is it an effective way to
yeah.
communicate
My
with
thoughts
God?
on my thoughts on prayer are complicated. I hope I get them right. I mean, I hope I can explain them. I don't believe in prayer for selfish things, where I say, I want to pray in order to get an advantage, something. I think of prayer as conversation with God, that I would, even if I didn't know that prayer was effective, I would do it anyway. It's just something that feels natural. When I was a child, I thought about prayer in a very selfish way. I mean, I remember rather quite vividly, hearing that if you ask God for something, He'll grant your wish, and I wanted a Ferris wheel. And I went to sleep and I said my prayers and I said, please God, put a Ferris wheel on the front lawn tomorrow morning. I'm serious. And the next morning I ran to the window, expecting to see it there, and it was very shocking to me that it wasn't there. Now that I say is a completely wrong attitude to prayer, but it was something that I had. But now, no, it's a conversation. I hope that God will do something, but I don't do it in order to get an extra thing about it. It's just something that I feel like doing, the way I feel like hugging my wife sometimes. I don't know. Yes.
Deterministic world, let's say two brothers exist.
Excuse me?
In a non-deterministic world, let's say there are two brothers, they're twins, and their behavior cannot be predicted, but if you look at the correlation between them, they have a perfect correlation. So if you observe one's behavior, you can know what the other is doing at the same time. Or let's suppose they have 90% correlation in their behavior with each other. Do you consider individually each of them have a free will, or do you consider together they have a free will? Or
Okay, so your question is if there are identical twins who tend to make the same kind of decisions with 90% correlation, are their wills correlated somehow? I have never known of twins that were correlated in this way. I mean, I know that there's things that about the way the way people move when they get up out of a chair and things like that that definitely seem to. But I haven't known that they're being their personalities or things were that way. But if it's true, then there's certainly reasonable to imagine that either that their souls are correlated or that their consciousness without a soul is governed by a very similar mechanism. Yeah, but I don't have any personal experience with that kind of thing. Doug?
Sometimes our free will gets tangled up with the real world, and the simplest example I know of is the fact that you so often get documents that say this page intentionally left blank. Yeah. And then I realized finally that it was really just how do you solve that problem in a proper way, which is to say this page was intended to be left blank. You have a comment?
The sentence on this page is false. Yeah, okay, yeah.
This is not one of those.
Yeah, okay, yeah, so you have to try to explain, there are a lot of paradoxes of this form where people try to will themselves to do something that they can't. It's like the people in Smolyan's story tried to will themselves to laugh by, without really getting the idea of laughing. And I guess that's the kind of thing you're referring to.
Except is it not a solution to it when I give?
A solution.
Yeah.
Well, certainly your solution was absolutely wrong because this page was intended to be left blank.
But I couldn't give you this message that, see, as long as you gave up that you wanted to have somebody not worry about the blank page.
Yeah, no, you got, what you have to say is the other page was intentionally left blank. Okay, over here. Oh, I thought I saw a hand up. And somebody want to ask me what I was going to say that I promised last week that I didn't get to. What?
Just sort of trying to tie things together. A lot of the comments you've made today, in a sense, seem to be along the lines of on the one hand, clearing away sort of logical objections that some people would have to the existence of God, and on the other hand, particularly, at least for you, resonant images or metaphors or whatever that help you conceive of God. And I guess the gap I'm experiencing a little bit is my own experience, at least, was of kind of coming to a religious sensibility in a much more experiential way, that I had to get rid of some intellectual objections, although probably not as erudite as the kind of things you've been mentioning, but that the various comments don't seem to sort of connect with that experiential aspect or relationship aspect of religious belief and experience. Yeah. I don't know, it's not so much a question as maybe a point of departure.
So the question about the experiential things about religious experiences. So I focused in my talk on the things where computer science would add to some things that I had seen in other discussions, and so when I read other discussions, I say, well, you know, how about thinking of this? Why didn't you bring up this point, which it seemed to me a computer scientist would bring up? Now, one of the things I did while I was here I read on some things that in my Bible study I was learning about ecstatic experiences that people had, and I wanted to pursue. For example, I'd heard that Plato had talked about something called divine madness, or which the Greek word theomania, and so this is a God-given state of being besides oneself, and I found that Plato had discussed already long ago that he noticed 4 kinds of such activity: prophecy, catharsis, poesy, and eros, so I learned a little bit about that some reading that I was doing in the past weeks, but I didn't see how to bring it into this lecture, except unless somebody asked me the question. The thing I promised to talk about last week had to do with some experience I had when I was designing a chip. But I decided it probably doesn't relate so much to God as to economics, and so. But it's a little bit about dealing with or thinking about the universe, however, and that is it surprised me that the easiest way and somehow the best way to design his chip was to have it doing all kinds of things that would never be needed afterwards. The input, there would be 2 input numbers, and the adder would add them, and the subtractor would simultaneously subtract them, and the multiplier would multiply them. And these things were all going on at once inside the chip, and then only one of these things would survive and actually be used in the computation in the next step. And so that seemed to me a kind of the reason is to design the chip so that everything that inside the multiplier has extra gates on it saying don't multiply unless I tell you to. Adds an awful lot to the hardware. And well, I started thinking about this, a metaphor for society and the world in general. What if, this is a reason for people to do things, even though only 1,000 people to work on a problem, even though only one of them is going to solve it, or if even though they know in advance that only one is going to get the answer. So people can so people can take pride in working on stuff even though it never gets out the door. So I was going to muse about that a little bit.
Sort of like it's easier to let people make mistakes than to have such a tightly controlled system that no one can make
let people make mistakes instead of saying, well, I remember something Dijkstra told me once. His first visit to Stanford, he saw the linear accelerator, and he just couldn't believe that so many experiments were going on simultaneously. To him, you should run the accelerator for an hour and then sit and think for a year about what you learned, and then turn it on again. And the other attitude was the American way instead of the Dutch way. So yeah. Okay, back there. What? You're running?
So we could probably go on forever, which is a good demonstration of every week you have answered a lot of questions, raised at least 10 times as many new questions. And that went on and on and on for so many weeks that now we are left with so incredibly amount of number of questions. And this is probably the biggest success of your talks.
It's not to answer, but to raise them.
Yeah, that's probably the wisest thing to do. And for the audience, the lectures will be published at some point, hopefully in spring or summer, depending again on time and money. And particularly on Don's time, who said that's his goal, clearly said, is to finish the art of computer programming. And that has precedence before everything else, and I can certainly understand it, as will probably have everyone else use. I hope to continue this program. Unfortunately, it will not be done. So we have to say here and now, Don, goodbye, and thanks again.
Okay, well. Thank you again, Anna, for inviting me. Thank you all.
That was such a beautiful ending.